Here we'll start to learn about where the internal energy equation comes from. So we're going to start by considering thermodynamics, and in fact the first law of thermodynamics. The first law of thermodynamics says that du plus P dV, where U is the internal energy, P dV, P pressure, V volume, is given by dQ. Internal energy combined with PdV work gives you the heat of the system dQ. And these D's here, they mean changes. And it's easy in thermodynamics to get hung up on what the D's mean and sort of what they're related to, but just think of them here as change. In fluid dynamics, the D's will almost always go to Lagrangian derivatives when we move on to as we move on to a PDE for the evolution of the internal energy. So don't get too worried about these infinitesimal variations here, the D's. So our U, this is the internal energy. P, this is the pressure. V is the volume. And Q here is the heat. The first law, it links pressure, volume, internal energy, and heat, and it's changes of volume and heat that lead to changes in internal energy. Now, the first law here has two types of variables, two types of thermodynamic variables, and these are the extensive and intensive variables. And to understand these and their role, we're going to briefly digress. So let's start with the extensive variables. So what is an extensive variable? Well, according to the IUPAC, an extensive variable is a variable that changes in magnitude when the system size changes. So magnitude changes when system size changes. So examples of this are things like the total internal energy, the volume, or the amount of heat in the system. Those are all extensive variables. Now the other type of variable we have are the intensive variables. And again, from the IUPAC definition, now the magnitude does not change with size, with system size. And examples of this are, for example, temperature and pressure. We think in some senses of the extensive variables as like global variables that kind of describe the global state of the system, and we think of the intensive variables often as local variables that describe a system in kind of a local sense. As an example of intensive versus extensive variables, if I have a Nalgene of water here, whoop, whoop, and I take two of them. I take two Nalgenes of water, make myself a nice little Nalgene. Nalgenes are kind of a nice fiducial liter, and I pour them into a bucket of water. A larger bucket. So here's 1 liter plus 1 liter, and I end up with 2 liters of water. The volume has changed. it's gone from 1 liter from one Nalgene, 1 liter in each Nalgene, into 2 liters from the combined system. But the temperature has not changed. The temperature in the bucket is still the temperature as in either Nalgene. So the volume is an example of an extensive variable, whereas the temperature is an intensive variable. All right. So we're going to switch actually from the extensive variables of the first law. Our first law up here, these du plus p dv equals dq, those are all extensive variables. So we're going to switch from an extensive form to an intensive form, which ends up being a little nicer for creating the partial differential equations from. So we're going to do a change of variables. We're going to go from extensive to intensive. And we're going to do that by using the mass. So we're going to say that the U is the mass times a lowercase u. We're going to say that the volume, this is the mass for an element times a little lowercase v, and our heat is going to be a mass times a lowercase q. And we give these intensive variables a special term that you'll see a bunch. We call this the specific internal energy. We call it the specific volume and the specific heat. And this is the internal energy, the volume, or the heat per unit mass in the system. The m's here are unit masses of the system as a whole. So that u, little u, right, this is equal to big U divided by the mass of the system. So this is the total E internal energy over the total mass, and that's the internal energy per unit mass. All right. Now in this form, I want to write our first law of thermodynamics in this form. So we'll come down here. So we're gonna switch to our intensive variables. So this is d little e. I'm going to move the pressure term to the right-hand side. This is dq, and now minus p d v. P is an intensive variable, so we didn't change it. And this v here, recall this is the specific volume. Okay. And this specific volume, this dV, I want to consider its properties just for a moment. So the specific volume itself, this has units of volume per mass, and that's just 1 over the density, since the density is mass per volume, and this means that dV, d specific volume, this is d 1 over rho, right, which is d rho to the minus 1. D rho to the minus 1, this is equal to d rho divided by rho squared with a minus sign out front, and by our identity for logarithmic derivatives, this is 1 over rho with a minus sign out front, d log rho. And this will be handy in just a moment. All right. So let's come back up and use this in our internal energy equation. So we have that dE is dQ, the change in specific heat, minus p dv, but that's plus now p d rho, or excuse me, that's, let's keep our sign straight, minus p d rho to the minus 1, because dv is d rho. And then this is dq. And when we put in our identity for d rho here, this becomes plus p over rho d log rho. All right. What's next? Well, let's change from our current form of d's. Let's recognize that our d's are actually Lagrangian derivatives. So that, again, as a reminder, that's a partial with respect to t. That's our Eulerian derivative, plus an advection term, u dot grad. All of this operating on something on the right-hand side here of this operator. All right, so the Lagrangian equation for the internal energy is d E dt is equal to dq dt minus p over rho, and then, or excuse me, plus p over rho let's get our Lagrangian derivative in here correctly, d log t, or d log rho, big D ln rho dt. We've not assumed anything here about this being an ideal gas or anything else. This is the internal energy equation for a fluid following the first law of thermodynamics. That is all. All right, let's clean this up a bit. Let's use the continuity equation to take care of this d log rho dt. So from continuity, we know that 1 over rho of d by dt of rho, so this is d log rho dt, well, this is equal to just minus the divergence of the velocity u. It's 0 for incompressible motions, and if we compress a flow, then the log density changes as the divergence of the velocity. If we now put that into our internal energy equation, we get our next form. We get that the Lagrangian internal energy equation, dE internal energy, dt, is equal to dq dt plus p over rho, but then it's d log t, so this becomes minus p over rho times the divergence of velocity u. And we're almost done. Now we just need to think about what dq is and represents. What of dq? Well, to get a handle on dq, it's often useful to appeal to the second law of thermodynamics. And the second law of thermodynamics says that dq is related to t ds, where s here is the specific entropy. Or the entropy per unit mass. If we now put this into our equation, we can get a closed form for our system. We get that d E dt is equal to t ds dt minus p over density rho div u. Put in our vector signs. And again, we've assumed that this is a fluid following the first and second law of thermodynamics, but we have not assumed that it's an ideal gas. So this comes from the first law and second law of thermo. Now, why did we go to the trouble of changing dQs into this TDS form with entropy? Well, this lets us observe something right away, which is that if we have an adiabatic class of motions, so these are typically motions that are very, very fast. So if adiabatic, if we have adiabatic motions, then ds dt goes to 0. And if we have adiabatic motions, we can simplify our internal energy equation to say that dE dt is equal to just minus p over rho div u. So this is this nice, clean, simplified form under the assumptions of adiabatic. To make any further progress and to model a real fluid, we need to come up with a description of the internal energy in terms of the pressure or temperature or other thermodynamic variables of the system. We need, again, an equation of state. But this equation here is fully valid for all of the fluids it will be considering. It is not yet restricted to a special class of equation of state. You would need that to actually solve the system in any practical way.